All right, so this is hopefully a very easy question for all of you. So we got a coin tossed, it came up heads 10 times in a row. What's true about this? Okay, so all right, law of large numbers says nothing about what any kind of short-term behavior is. Law of large numbers says that if you have thousands or millions of iterations of this particular event going on, you would end up with a relatively stable kind of proportion of successes. And it doesn't care at all about short-term trends. So I'm getting this to work. So according to the first one saying the next one is more likely to be tails and other heads, the basic takeaway, the probability doesn't change. It's still 50-50. By the properties of conditional probability, the next toss is more likely to be heads, given that 10 tosses in a row have been heads. Nope, it's still 50-50. Coins actually do have memories, and thus what comes up on the next toss is influenced by the past tosses. Probably the stupidest answer here. The law of large numbers tells how many tosses will be necessary before the percentage of heads and tails are again in balance. This one's somewhat tempting, but the law of large numbers doesn't actually say how many tosses are going to be necessary. It doesn't really say anything about that. Like I said at the beginning, it just says if you have a lot of iterations of this, you're going to get kind of a stable spot that it lands at. But it says nothing about specific numbers. Hey, what do you know? None of these are true, which is, I hope, exactly what everyone was thinking. So we're looking at chi-square test for independence today. The last part of class is going to be figuring out which chi-square test to use. I have just a few scenarios. We're going to look through it. And I am going to put you guys on the spot a little bit today, just giving you a heads up. You're going to have to do one of these problems of chi-square test for independence. So as we're getting started, the first thing we need to talk about is kind of remind everyone what independence is. So we've got the definition according to probability. It's been a while, so let's kind of go through it. So we've got the probability of A is equal to the probability of A given B. And if this is true, then the events are independent. And let's kind of look, I'm going to start with the one at the bottom right here. In fact, this is an example that we used before in the past. So this will hopefully look familiar to you. Not that you need to remember the example. So if we just focus on, this is maybe some kind of a class. So we've got pass or fail. Let's say we're going to find out the probability of passing a class. That's going to be my event. So the probability of pass is just going to be 120 out of 200, 120 out of 200, which is 0.6. So now let's kind of look at a contingent probability. And this is going to be, what's the probability of passing a class given that you're male? So probability of pass given that you're male. And this is now going to be 66 out of 110 because it's a contingent, contingent probability, conditional probability. That's the word I was looking for. So 66 out of 110, if you do that math, turns out, well, that's still 0.6. So the probability of passing is equal to the probability of passing given that you're male. Therefore, these are independent, all right? It meets this. So independent means that there's no association between gender and whether or not you pass the class. Those two variables are independent of each other. Knowing one tells us nothing about the other. No association. So that's kind of the idea. If it's independent, that means no association. Which means if it's not independent, that means that there is an association. All right, so that's kind of a little bit counterintuitive to think of it that way. But anyways, now if we look at the other, the probability of preferring dogs is 51 out of 100, which is uh, 0.51. And so you can see that's 51 out of 100 right there. Now the probability of liking a dog, given that you're female, according to this sample right here, is 9 out of 48, which is, if I remember correctly, I did this math earlier, 0.1875, I believe. So these two, the probability of A and probability of A given B, definitely do not equal each other. So these are not independent. There is an association. At least according to this data, we could say whether or not you like or prefer dogs or cats is dependent or is associated with your gender. Okay, so I think this is a totally made up data set, but I think it's just to show really clearly two not independent variables. All right, now well, I'm jumping a little bit ahead. Let's kind of see what the next page talks about. So in our chi-square test for independence, we're going to precisely quantify what we previously only kind of estimated or, kind of did these close enough sort of calculations. And as a reminder, our former rule was that if the percents were within about 3% of each other, we decided that the variables were independent. So if I had a probability of A of 0.57 and a probability of A given B was 0.591, what we would have done in the past is we would have said, that's close enough. Sure, they're independent. And therefore, there's no association. That's where we left it before. Of course, now we're going to precisely quantify if there is an association or not. All right, and it's an inference test. So when I say precisely quantify, we're going to make it certainly more quantified and calculated and more mathematical, but still we have two options. We're either going to accept the null hypothesis or we're going to reject it. So there's still a little bit of gray area where it's like, oh, is it a type 1 or type 2 error? Maybe so. But anyways, we will be a little more precise than we were before. So kind of rehashing the last slide, the probability of a person passing a class, that bottom right example, was independent of gender. So they're equally likely to pass a class no matter whether they were male or female. There's no association. And whether person, I guess, preferred cats or dogs was not independent of gender. And therefore there was an association. So that kind of wraps it up. Here's the definition from the textbook. Again, this can help in some ways. I'm not actually going to sit here and read it, but one of the takeaways is that we're looking at one group of individuals. So one of the key ideas of a chi-square test of independence is that we are taking one sample and testing two variables on it. So I collect a sample and now I want to compare, gender and animal preference. So I'll just put pref right here for preference. So those are two variables that I kind of extracted from the one sample that I got, and I'm comparing these two to each other, and I'm determining, is there an association between those? So this is how we use a chi-square test for independence, which is a little different than the homogeneity test we did yesterday. In that test, we had one variable. So I had two samples that I took. So these circles represent the samples. And now I got I basically got response on one variable. And now I wanted to compare these two and say, did the response from, this is sample 1 and this is sample 2. So did A sub 1 and A sub 2 end up the same? Are these two homogeneous populations, or basically that we're sampling from? Or are they two heterogeneous populations? So that might help you think, keep it straight of when we're using homogeneity. And so of course, this is labeled wrong on here. So if we switch these two labels, Independence is when you have one sample looking at two variables. Homogeneity is when you have two samples looking at one variable. So sometimes it's going to be really obvious, and I'm going to give you some ideas about what you can look for to kind of decide if it's a homogeneity or an independence test. That's going to be the hardest decision to make in this whole process. Again, practically speaking, there's no difference in how we approach it. The calculations are all the same. The only difference is going to be what our hypotheses are and what our conclusion is. So really, that's what it comes down to. But anyways, kind of an example that I made up earlier that was just really, really obvious that it's going to be a homogeneity test, just to kind of get you thinking about that for a second. If you went to two different places, and I was looking for places that you might expect to see different crowds show up. So if this is a football game, and then you went to a symphony, and then you asked them a question, maybe on a really controversial topic. So I just threw out, what if we asked them a question on gay marriage? Do you support gay marriage or not? All right. If it's the same population, we're basically asking about gay marriage. So I'll just put that right there. So now I want to compare their results to see if it's really the same population and they're homogenous and they just, one likes symphony, one likes football, or if it's a different population, or there's a difference in the population related to that. So hopefully, I'm focusing on homogeneity right now because we're about to contrast that with our independence. Okay. So independence, one sample, two variables. And here's our example. It's a little silly maybe, but it gets the point across. So if you are looking at a sample, in this case, I'm just going to jump to the sample. It's a random sample of 600 senior students, okay? So if you look at that sample and you could find out for every single person in that sample, can you do, they're calling it taco tongue. So basically, can you roll your tongue into a loop? Some people can, some people can't. And then separately asked, can you do the evil eyebrow where you raise only one eyebrow? And maybe all of you now, since I can't see your videos, maybe a lot of you are trying to turn your tongue into a loop and seeing if you can raise your eyebrows. Oh, we got some examples of this happening in real time. How exciting. We're gathering data. All right. So the question is there some kind of an association? Like if you can do the taco tongue, you're more likely to be able to do evil eyebrow, or does it not depend on that at all? So this is, I'm assuming this is all made up data, but maybe you can figure out if you can do one or both or neither or all that fun stuff. Okay, so these are two variables collected on every single person, and let's kind of run through this process. And I actually want to jump to the next page. So our hypotheses, the hypothesis is for a test for independence is always going to be like so. The null hypothesis is that there is no association. Which is really a way of saying that they are independent. But anyways, there's no association is the null hypothesis. And we can add some context. There's no association between taco tongue. Just it's weird to write that. Taco tongue. But it is shorter than saying being able to put your tongue into a loop or whatever. Between taco tongue and evil eyebrow. Okay, there we go. The alternative hypothesis, you guessed it, there is an association. I won't write the whole thing out, but we got that. Significance level, if not told what to use, just use your good old trusty 0.05. Pretty straightforward. Of course, this presentations available for you. And in here, you'll see all three of our chi-square tests and what the hypotheses should be. For today, null, no association. Alternative, there is an association. So this is going to be, I'll tell you now, this is going to be one clue to look for when you're looking at the problem. If it's asking about an association between variables, then automatically you're like, okay, it's chi-square test of independence. That's what I'm doing. So that's going to be a nice word to be on the lookout for. Okay. Name of the procedure. Okay, this should have fixed that. It's not the goodness of it. This is for independence. The conditions don't change. Is it random? Is it 10% and normal? All right, so random. If you recall, I underlined it before. We saw it was a random sample of 600 seniors. So yes, and here's where I might even write random sample in quotes. And when you put it in quotes, that means this was actually from the question prompt. So yes, 10%. There are 600 seniors, and that is so 600 is definitely less than 10% of the population size. So I think that's good to go here. We can generalize this to, at the very least, all seniors. Okay, and normal. Remember for this, your lowest expected count must be greater than or equal to 5. So we have a slightly different normal criterion that has to be met. Let's go ahead and figure out all of our expected values. We're going to need it anyway, so we might as well do it now. Remember, we want to take, for this equivalent cell, we want to take the row total, multiply by the column total, divide by the table total. Okay, so if I do that, that's 480 times 200 divided by 600, and we get 160. All right, for the next one, it will be, now that 300 right here that I just circled doesn't matter, but it's just to say this row total is 480, 400. You multiply those together, divide by 600, and you'll get 320. We can do a little bit of a shortcut on this one. Not that I think you should do any shortcuts on this. It's easy enough to do the calculation, but if we're going from 200 to 400, then we can just double our values. Plus, we could also take the total, subtract away this value we just got. Anyways, I'm not sure that you should focus on shortcuts. I'm just showing you. So if we multiply this one out now, let me erase over here. This cell is going to be 120 times 200 divided by 600, which will be 40. And then whenever we do this same thing again for this one right here, 120 times 400 divided by 600 is going to be 80. All right, and just to make sure it's very, very explicit on this, 120 times 400 divided by 600. Okay, so that's a calculation I did, and we'll see that spelled out on the next page. So there we go. Now it's really, I showed you those shortcuts, like, oh, you just take 480, subtract 160, you get your 320. Now, you shouldn't necessarily do that shortcut, just do the calculation. It's not that hard to do. But it is still good to, at the end of this, when you don't, especially when you don't have these nice whole numbers to work with, it's really good to go ahead and add up along your rows and make sure you end up with the correct row total. And then add up along your columns. Make sure you end up with the correct column total. And that's just a really key step in this to make sure that you don't end up working with wrong expected counts and therefore you get wrong answers. Okay. So I will leave those numbers there. I'll just erase this writing down below. We'll move ahead. You can see our conditions right here, all well and good. And of course, our expected counts for each cell will be calculated thusly. Okay. Our specific formula for all chi-square is going to be the same. Chi-square is equal to the sum of observed minus expected squared over the expected. And remember, for this, it's just as easy to kind of run through, do all the calculations on the calculator, plug the values in, and then later we'll come back and add the work. So I'll leave this right here. You guys can create your matrices. We had to do this yesterday. Create your matrices, come up with your answers, and put the answers down right there. And I'll leave that available for you. All right, so we got our chi-square and p-value found. That's good. There could theoretically be a question. One thing it doesn't ask you to show anywhere here is where your degrees of freedom are. So of course, it's not a bad idea to just throw in that you have 1 degree of freedom. But if it, you could theoretically have a question where it gives you this really long prompt. You have a bunch of writing. It gives you this two-way table, with just an insane amount of cells in it. And then you need to read through because the question could simply be, what's your degrees of freedom? And assuming this is not your marginal totals, this is all just the conditional distributions in the middle, then you may be like, oh, all it wants is degrees of freedom. That's pretty easy. It's going to be 1, 2, 3, 4, 5, 6, 7. So 6 times 1, 2, 3, 4, 5. So that's going to be 4. 6 times 4 is 24. Basically, this represents your degrees of freedom. Everything except the last row and column. So keep that in mind, that you need to know how to find your degrees of freedom. All right. Now, the other thing we can do is show our work. We can start with the very first and go to the very last cell, but we can ignore the others. And so this is an important point. We have an observed and expected value for our first calculation, our first chi-square calculation. Or component calculation, I should say. So it's going to be 180 minus 160 squared divided by 160, which is the expected value, plus put your ... Now, I'm going to have you guys write out your work later in class. Don't forget these pluses. This is showing that you're creating a summation, this part right here, and you're adding up all the different components of this. So you have to put the pluses there. And then the last one is 100 minus 80 squared divided by 80. So that shows, okay, here's the list of all the different calculations I would do, add it all up, and I get my 18.75. Now this equals 18.75 isn't absolutely necessary, but it's good to show it. All right, so for the picture again, I'm not going to try and come up with that on my own. What I'm going to do is I'm going to run that test again, go back to chi-square test, but when I go to the bottom, I'm going to have it draw. And the most important thing for this is I want to make sure I show the correct chi-square distribution curve, which looks like a power curve. All right. And I can just show, because it really doesn't even show up on my calculator, but I could show like maybe right here, this is my chi-square value, 18.75. And then this right here is my p-value. All right. I can just kind of do something like that. So there we are. We shown a picture, we did our work, We've got all the values of note. Okay. So this is just to wrap it up. You can see, again, your degrees of freedom found right there. And now we can conclude. So our conclusion is going to be related to the hypotheses, but we of course start off the same way every time, because the p-value was less than the significance level. And in parentheses, I'd want to put those numbers, but I'm going to be a little bit lazy. Oh, I could write in the 0.05, I guess. So whatever this number was is less than 0.05. We reject the null hypothesis. And yeah. We have convincing evidence. It's turning less and less into a word the more I write. We have convincing evidence that, and here's where I can just go back to the prompt. Do we have convincing evidence that the ability to do the taco tongue and evil eyebrow are associated? We have convincing evidence that the ability to do the taco tongue, I don't want to capitalize that, and evil eyebrow are associated. And this is where we kind of need to, you might have to stop here and think about it for a second. So our alternative is that there is an association. We have rejected the null, so now we have convincing evidence that the alternative is true. And so we're kind of saying it this way. We have convincing evidence that there is an association. Okay, so if you have to go back and refer to your null and alternative hypotheses in order to get this part right, no worries, no problems there. Okay, so that is the process for a chi-square test for independence. And we're going to jump into another problem, but here is what we're going to do for this one. We're going to do a little differently. I want you guys to do this problem. And that means we'll kind of do it as a class, but I want you guys, someone to tell me what the hypotheses for this should be. I guess it doesn't technically give you a question, but we're basically asking if there's an association between your survival probability and the class that you stayed at on the Titanic.
There is no association between survival and class.
Okay, I'm just going to say no association, which means our alternative will have to be what?
There is association.
There is an association. All right, pretty straightforward. What should our significance level be?
.05.
0.05. Good old 0.05. Why not? All right, pretty straightforward on that. Again, there's a typo here. Actually, we'll do this part with you guys or we'll talk about it. Because this one's a little bit weird. Chi-square test for independence. Random, 10%, and normal. So we'll figure out normal in a minute. I'm going to have you guys figure out the expected counts. But my question, this is where it might be a little weird. Random and 10%, what would you guys say about this?
I would say it's not random.
Okay. And what about that 10% condition?
I don't think it's 10% of the population.
Yeah, it's not like this is something that we can generalize to all ships, and especially all ships that sink. I think this is kind of unique to the Titanic. So here is, for these two, if this is actually an AP question, you might say something to the effect that this is kind of a census of the, and if you just kind of note that, we're still going to use our methods that we're using now. But if you kind of said something to that effect, it's like, well, really, this is a census of everyone who is involved, which is what a census is. So maybe this one's a little bit strange, doesn't quite work for meeting our conditions for this particular test, but we're just going to go with it. Okay, so for normal, of course, we need our lowest count to be greater than or equal to 5. We're going to need to do this anyway, so I'm going to put this in the bottom corner. And I want you guys to fill in this table with all of the expected counts, and we'll make sure that we meet our normal condition. While we're getting the last numbers put in, we can answer the question. Did we meet the normal condition for this one?
Yes.
Yes, we did. With a plum. Okay. Lowest expected count here was definitely greater than or equal to 5. So we are good to go on that. All right, so that one's good. I'm going to show what I got right here. I got 478.26. All right. Where's that 0.28? Yeah, oh no, it's 0.26. But anyways, this is all close enough. We're off by maybe 100th here or there, but that shouldn't affect too much. All right, so very good. We have all of our expected counts now, which is going to be probably the most time-consuming part of these problems. Maybe putting in the matrices will take a little bit. And now we can move forward. Maybe some of you have already anticipated and started doing the matrices, but here's what I want you guys to do now. I want you to go ahead, plug this in, do the work. I'm not going to write anything on this page unless I need to. So I want you guys to fill in the formula, the picture, the work, the test statistic, the p-value, even show your degrees of freedom right here. Why not? Just for an extra bit of fun. All right, so go for it. So this is really good work all around. Now the picture, the one thing I would do here, and maybe just didn't have time to finish, but you want to show where your chi-square value is. And this is just approximate, just to give an idea. I know that my chi-square value at 187.79 is going to be way off the chart, but just to show that this is chi-square value, you can just write chi-square, and then you're kind of drawing where your p-value is. Can't quite fit that on the screen. Just to kind of give an indication that this is way, way, way out there, very low probability. The other thing, and this is more of just like, just to make sure it's very, very clear, sigma right here being in the numerator is very different than sigma being off to the side. So, and this is just be careful how you write it. I don't think when you wrote this, you were intentionally, there you go. That can fix it right there. So just make sure it's very clear that it's the sum of all of these calculations, So that right there. So anyways, that's about it. Good work all around. We got a very, very low p-value. This is one of the most extreme p-values we've ever seen. All right, so now we can make a conclusion. Well, before we do that, we had 3 degrees of freedom, and you could easily calculate that one by hand. And we can see 187 is just so far off the chart here. but if you had to use this, if for some reason you're forced to use the table, you could say it's less than 0.0005. Okay, so now if we could just verbally say what our conclusion might be.
Because the p-value is less than the significance level, we reject the null hypothesis. We have conclusive evidence that we have conclusive evidence that the I don't know how you like the amount of
Well, anyone
alive
else?
people is not or is associated to the class.
There you go. Okay. So you basically got the point across, and that's good. You can phrase it different ways, but we have conclusive or convincing, not conclusive, convincing evidence that there is an association between variable 1 and variable 2, however you want to call those variables. But you had it right. I think you got the idea across and how you phrased it. Okay. So very good. For the last little bit, I'll go ahead and clear the whole screen now. We don't need those calculations anymore. For the last little bit, I'm going to give you guys a few scenarios. I want you to read it and determine, are we looking at a goodness of fit test, a homogeneity test, or an independence test? So first one, just circle it whenever you determine which one it is. All right, so this one is a tricky one, but it's only tricky the first time. This is where I want you to, this is just a simple trick you can use moving forward. One simple trick. So notice in the prompt, it says we have separate random samples that were taken. So this tells me there were 2 samples. So this is where we want to look into the wording of the problem, because what we actually have here is store A and B represent 2 different samples that we're comparing. And again, practically speaking, it doesn't change any of our calculations, but it does change our hypotheses and our conclusion. That's about the only thing that changes. So this would actually be a homogeneity test. All right, and this, I mean, I don't love this particular example, but it does at least help get across the point. Read the prompt and see if it even explicitly says there were multiple samples taken, or if it says it was 1 sample. Okay, so we're good with that. Here's your next one. All right, so this would be an example of a chi-square test for independence. That's correct. And again, even if nothing else, you could say, okay, it was only 1 sample. So that can be kind of what you base it on. But then if you look at it, and this is where you just have to be careful sometimes. Even the example, one of the examples we used for homogeneity yesterday might have been better off as a test for independence, but it was technically 2 different samples, and so it was fine. But anyways, yeah, this right here is a variable about all the people in the sample. This is a variable about them as well. And I know there's kind of this gray area where you could kind of say, well, anything's a variable. So you just kind of go with what makes the most sense for the given scenario. But it was 1 random sample, and then after the fact, they separated these people into the type of degree held and then their opinion on astrology. So it's a chi-square test of independence. Very good. All right, sorry about that. So now the last one, go ahead, figure out what kind of test this is going to be. Okay, now, yeah, we've already seen an example of homogeneity and independence. So goodness of fit is the last one to look at. But keep in mind what we're doing with goodness of fit is we're saying, here's an observed distribution of outcomes for 1 variable, 1 sample, and then we're going to compare it to what it should be. In this case, we have a theoretical probability to compare it to. We've got 18 red, 18 black, and 2 green. So we can actually go through, this is a total of 38 slots. So I know that my theoretical probability for all these is just going to be to divide by 38. And then if I want to figure out my expected counts, I can just multiply each of these by 200. So all these will multiply by 200. And then I can figure out the actual expected that I'm going to compare this to. And this is kind of a standard that I'm holding it to. So I wouldn't consider it as a homogeneity. It would be a goodness of fit. All right. Now, here's what I highly encourage you guys to do. You have enough information here to actually go through and perform these tests. We're not going to do that right now, but you can certainly feel free to come back to this presentation, look at these problems and run through and do these to make sure you're good with the full process. The other thing, now this is your homework. And I, of course, want you to do all the homework, and you're going to have to kind of think through what type of test to use. You can always go to the back of the book, make sure that you're deciding correctly. But the other thing I would highly recommend, and I was looking online for a resource that just has like 20 different prompts for you, and then you kind of had an opportunity to go through and check to see what kind of test was appropriate. I couldn't find anything like that. So all the problems that I did not assign you, go through and look at them just to kind of answer the one question: what kind of test should I use for this problem? And if you can answer all those correctly, then that's going to help you kind of with all the kind of stuff. But there you go. There's your homework. On Monday, we'll have our test. If you have any questions, you can stick around. One thing I was supposed to encourage all of you to do, hopefully while I have your attention, is if you haven't updated your iPad yet, please do so and make sure you're at least at like 14.1. And that way you can start deleting your certain apps at that point. All right, but besides that, if you have any questions, stick around. If you're good to go, have a wonderful day, and I'll see you on Monday.